now we will discuss about helical turbulence, fluid only. So, here there will be helicity, kinetic helicity. So, flow with kinetic helicity, okay, and we will control that. So, let us brush up our earlier knowledge about kinetic helicity. So, I will just do this outline: conservation laws, kinetic helicity transfer formula, mode to mode transfer, then phenomenology of helical turbulence and numerical results. So, this short discussion. Conservation laws. So, let us focus on it. So, total helicity is defined as u dot omega. Okay. So, this is I did mention it. So, these are like screw like velocity configuration. So, is very similar to circularly polarized waves. So, u dot omega, if it is positive, then it is positive helicity, negative is negative helicity, okay, or it could be 0 as well. And for viscosity equal to 0, if you have viscosity 0, then total helicity, total kinetic helicity is conserved in 3D. Of course, in 2D is 0, right, omega is along z and u is xy, so it is 0. So, let us look at in Fourier space. So, Fourier space, this is a formula, right, I mean real part of, so its quadratic becomes dot product of, it is a modal kinetic energy for a given mode, but one of them must be complex conjugate, okay, take the real part of it, and I did derive this stuff. So, real cross u imaginary, so k dot real, so you have to have both real and imaginary, and I illustrated by some examples, and if hk is maximum when both are perpendicular to each other, okay, so they must be perpendicular, otherwise you will get sin theta component, okay, and this was done before. So, we can look at the time derivative of hk. How does hk change with time? We need that for deriving mode to mode. So, modal kinetic helicity changes with time. So, I take the time derivative. So, I am turning off viscosity and external force. So well, I mean this was done before, if you look at your notes. So, uk you write its function of omega. So, is ik cross omega by k squared. I am not sure about the sign, but you can derive this, okay, this we did it. So, I substitute this one, this was so u dot omega, no, so u dot omega, so you just substitute u for that, and this is, so this derivation I have done it before, if you look at the slides, okay. So, this what we is equation for kinetic. So, we want to write it as omega omega, okay, there is a reason for it, it will become very clear. So, giver and receiver are omegas. Well, actually it is very hard to say. For kinetic energy we have uk and up, but kinetic helicity we have ua dot omega. So, who is giving and who is taking, right, because it is u dot omega. So, it is not the same species. So, that is why it is rewritten as omega dot omega in terms of omega. Now I write, so what is omega dot? Omega dot is curl of u cross omega, right, this is what is the equation for omega, curl of u cross omega. So, in Fourier it becomes ik cross u cross omega. So, substitute it and do some more algebra. So, we get this form. Now, this algebra I am avoiding, is there in the notes fully. So, so basically, so there is a k here, there is another k here, right. So, I substitute here, so this becomes k cross u cross omega. So, this k and this k will cancel with k squared, okay, and you get this u q and omega p, convolution, no, it becomes convolution. So, u q omega p omega k. So, now it is quite easy to guess how to construct a formula for mode to mode. So, this is not k dot u q u p dot. So, there is, so but it turns out I prove it again in the notes that you can, so you can basically satisfy all those energy or kinetic helicity transfer formulas, like A giving to B is same as B giving to A with a negative sign, and A B together giving to C is sum of A giving to C and B given to C. So, these are formulas and it must satisfy this relation for a triad. So, there are some subtleties, but I will ignore all that and I can write down formula for mode to mode. So, this with viscosity. So, this I am ignoring it right now. So, mode to mode kinetic energy formula is this. So, P to K prime. So, that is what we want, but is I normally write is way number P to way number K prime, not saying who is giving what, because U and U dot omega. So, P to K. So, the cross product of omega with omega. So, this is a giver, this is a receiver. So, omega cross product of giver and receiver, and mediator is just UQ. So, there is no wave number does not appear in this formula, okay, and it works well. We computed various quantities and it does a quite good job. So, this is a formula. If you want derivation, you can look at the notes, but I do not think you want to look at derivation. So, this you can use, fine. So, this I am giving you as a formula to use. Now, once I have mode to mode, I can compute various quantities like flux and shell to shell transfer. So, flux will be useful for constructing phenomenology for helical turbulence, okay. So, let us compute flux. So, what is the flux? We just usual helicity transfer from P to K prime, but P is a giver. So, flux was for a sphere, no, all the modes inside the sphere to mode outside the sphere, and the radius of the sphere is K naught. So, all the modes within the sphere are giver, this one, and all the modes outside are receiver here, and I made a mistake, less than equal to, okay. So, all the givers are within the sphere and all the modes outside sphere. Shell to shell. So, giver must be in the giver shell, a receiver must be in the receiver shell. So, we have two shells, this shell M is giver and shell N is a receiver. So, I want to see how much kinetic helicity goes from shell M to shell N, and we can compute them. So, helicity M to N. So, the giver belongs to M shell and receiver belongs to N shell, and you can just substitute the mode to mode formula which I showed you in the last slide, okay. So, you can compute all this stuff. Now, these are all coming from equations. I would like to see some properties. What is the spectrum for helicity? What is the energy spectrum when helicity is injected? So, you can have a run, or we have flow where helicity is 0 and a flow where helicity is non-zero. So, will combinatorial theory work for the energy spectrum? Will it be phi third or not? So, it turns out now this, okay. So, before we do that, so I want to tell one more formula because I need that one. So, we can also define this variable helicity flux. So, this is exactly like what we did for kinetic energy, no. So, we have this sphere, and so energy, well, actually from the sphere we derive equation for the shell, this shell of radius k, and okay. So, this is helicity in a shell. It can change by change in flux, very in fact identical. So, this argument for energetics are universal. You can apply for all sorts of this energy transfers. So, it is, so this shell can gain energy by the flux coming in and lose energy, lose helicity by flux going out. So, total will be in minus out, okay. So, this one, this is coming from external source. So, the external source, there could be helicity injection source, okay. Rotation is one good source for helicity injection, well, convection is, okay. So, convection injects helicity. So, there is an external force which can inject helicity, and dissipation can kill helicity. And this one, in fact, I should say that minus nu k squared hk. Hk is helicity for shell k, okay. So, this formula for dissipation is very similar to kinetic energy. There is a 2, I believe there must be 2. So, shall we go back? Let me just look at it here. DHK factor 2. So, there is a factor 2 here. Okay. So, it is like 2 nu k squared E k. Okay. Now, what if there is a steady state? For steady state, this one goes away. We assume inertial range. Initial range means this goes away. So, initial range steady state. For these two cases, I get basically 2 terms which is only function of k, not function of time. So, I get actually this is not partial, this okay, this function of, so flux will change because of dissipation. Okay. Now, if dissipation is weak in the initial range, then this becomes 0 and then pi h k will be constant. Similar to what happens for kinetic energy. Kinetic energy flux is constant. Okay. So, this is what we get. Now we are ready with this for our phenomenology. So, phenomenology turbulent helical turbulence. So, please remember I am injecting some helicity. So, how to inject helicity? So, there are some kind of this helical velocity field like circularly polarized, one direction more than other. So, there could be positive circularly polarized and negative circularly polarized. Okay. It turns out for kinetic energy there is a, no I am sorry I missed you Joe. So, there is a set of papers which we also did one work in long back. So, it turns out it is shown in these papers that kinetic helicity does not change the spectrum. It does not alter the nonlinear term significantly. Actually, it is not the nonlinear term. Yeah, it is basically the diffusion does not change. So, there is something called renormalized viscosity. Because of turbulence, it gets changed, but the change is same for helical as well as non-helical. So, the example which I gave in the earlier class, I believe, right. I mean, so the diffusion of dust particles is by turbulence, or heat diffusion is by turbulence, not by molecular diffusion. So, this turbulence will diffuse faster, will help diffuse faster. But if I put the same energy in the flow, but make it helical with the same energy. So, u squared is the same total, but u squared with could have u dot omega or may not have u dot omega. So, if u squared is the same for each mode, then this diffusion does not change. Okay. Now, this is a theory which I can't tell right now, but this is a theory. So, it does not really change the spectrum. So, this was what was proven, and so spectrum is same as Kolmogorov. So, EU of k irrespective of helicity, okay, k Kolmogorov epsilon into 2/3 k minus 5. So, irrespective of hk. Is it clear? The statement is clear. I have not proven it for this statement, and the flux will be same as what it was without helicity. So, energy only decides the flux, helicity does not. For kinetic energy flux, okay, is same constant approximately. Now, what about kinetic helicity flux and spectrum, which Kolmogorov theory did not say anything about it. So, let us try to derive helicity flux. Okay. Now, I will apply same kind of logic which I did for kinetic energy spectrum and flux. So, we are focusing on in the inertial range. Okay, steady state. So, inertial range means there is no forcing and there is no dissipation. So, what about the flux? So, I showed you that d pi h k by d k is 0. So, pi h k is constant, and that must be equal to epsilon h k. So, matching. So, whatever is injected at large scale is dissipated at small scale, but it is crossing this intermediate range. Same thing cascades. Is it clear? So, it is very similar to what I inject energy at large scale, it cascades, it is not generated in the intermediate range and it dissipates at small scale, fine. So, now let us talk about spectrum now of helicity. So, we denote it by Hk of k. So, this k is a shell spectrum, so energy in a shell k. So, dimensional analysis, what all could it depend on? So, it function of k as well as epsilon u, like before, kinetic energy flux or kinetic energy dissipation rate and wave number, but it could also depend on this now, or if you like in I think in notes pi u and pi hk, both are constants, this constant, this constant. So, I have 3 quantities which it could depend on. What is the dimension of hk, by the way? Hkk. So, hk has dimension of u dot omega. If I put this total helicity, if I put k, then I divide this by k, yes or no? So, anything spectrum you divide by k, you can do it blindly, because integral hk dk is hk, total hk. So, dk has dimension, so this has basically come down here, okay, is that clear? So, I will erase. So, u is L by T, k is 1 by L, omega is 1 by T. So, is L squared by T squared. So, right side. Now, so we have 2 mass is absent here. So, L and T, we have 2 fundamental variables. Now, I have 3 quantities. So, I can't determine all 3, right. So, you get only 2 equations by matching dimension of L and dimension of T. So, what do? I will make some arguments. So, this is not, well, this is the only argument which works. There is an argument from field theory as well, but we will not get into that. So, I will say this one pi hk is total hk by k, right. What about pi hk? The flux is total hk by time. So, we make an ansatz that hk, this helicity spectrum is proportional to pi hk. So, this and this quantity are proportional, because, so by the way, for things like temperature spectrum, it would be very useful. Temperature is a new quantity, it has additional dimension. So, temperature flux and temperature spectrum must be proportional, right, because temperature spectrum is theta squared by k, theta is temperature, okay, and many of you done this before, and temperature flux will be theta squared by T. So, these should be equal. In fact, I got motivation from this argument. You will find that this argument will also go to scalars like temperature spectrum. So, we will make this, one thing is that I will make pi hk. So, we will do it a bit later. So, this is hk of k is proportional to pi hk, we just make it like that. I mean, this is coming from one phenomenological argument. This is not rigorous proof, but it looks reasonable. And now we have 2 unknowns, k to the power beta pi u alpha, and which we can determine. Yes. So, this was an assumption that this exponent is 1. So, the left hand side is, I said, hk has dimension of L squared by T squared. This one has dimension of hk by T. So, this is what is u dot omega by T. How much is that? U L by T cube, right, L by T cube. So, 1 by T here, 1 by T here, and L by T cube, L by T cube. This is L to the power minus beta, and pi u is L square by T cube for alpha. So, what do I get? So, let us see, let us do the T first. T has one quantity less. So, T squared is 2 is equal to 40 2 equal to 3 plus 3 alpha. So, what is alpha? Minus 1/3. Now, what about beta? So, 2 equal to 1 minus beta plus 2 alpha. So, 1 minus beta minus 2/3. So, beta equal to 5/3. So, 2 goes minus 1 minus 2/3 is minus 5/3. So, Hk of k is pi of Hk k minus 5/3. So, let us put k minus 5/3 to the right, pi of u to the power minus 1/3 Hk of k of minus 5/3. So, this is my spectrum of helicity. So, it is similar to Kolmogorov, but this was flux to the power 2/3, but now overall flux has dimension of 2/3. This is plus 1 and this is minus 1/3, but they are not divided. So, there are two fluxes, helicity flux and kinetic energy flux. Helicity flux has exponent 1 and kinetic energy has flux minus 1/3. Okay. So, this is what we can derive from dimension analysis. We can also do from field theory, but we will not do it here. Okay. So, I derived all these quantities, kinetic energy spectrum, kinetic energy flux, which is same as Kolmogorov, no change, but kinetic energy flux is kinetic helicity flux is constant and kinetic helicity spectrum is 5/3 with dependence on both helicity flux and kinetic energy flux. So, now let us try to generalize it to inertial and dissipation range. So, what will I do? So, I will just give you the idea, and in fact it is very nice. We can derive the formula and it fits with simulation data very well. So, we again use this Pauwels formula. Okay, I have been pushing this Pauwels formula very much of late. Pi Hk by dk is minus 2 nu k squared Hk of k. So, what will Pauw say? Pauw will say that Hk by pi Hk is function only of pi epsilon Hk and k. So, I know only Hk already. So, is k minus 5/3. So, pi Hk was 1, no, power 1. So, if I divide, then that goes away. So, epsilon u 2/3. I will just get this. Okay. So, this is what I will get. Substitute it over there. So, if I just substitute here, what will I give? So, minus 2 nu k squared. So, this is going to be pi Hk epsilon u 2/3. So, this 2 and minus 4/3 will give you 1/3 minus 5/3. So, 2 minus 5/3 is 1/3 and and the epsilon u 2/3. Okay. So, it is the first order ordinary differential equation, okay, easily solvable. So, this k 1/3 integrate this, you will get k 4/3 with a minus sign, no. So, I write the answer. Pi Hk of k is exponential, you can easily make a guess, k by kd 4/3 and 3 by 2. I forgot to say that the constant in front for helicity is called kh, is not Kolmogorov, is kh, new constant kh. I will not go back to old slide. So, kh k minus 5/3. So, there is a kh here. Okay. So, these constants are basically from simulations, we compute them from simulations and also from some theory. Okay. So, there is some theory which, okay, and there is a epsilon Hk. So, there is an exponential drop. What about Hk. I can use this formula. So, this is just straightforward, Kh epsilon of Hk epsilon u of minus 1/3. So, I am replacing the fluxes by epsilon u's and epsilon Hk, K minus 5/3 and this exponential part. So, we got now formula which works for, which should work well, which I expect it to work in both inertial range and the dissipation range by just invoking Pauw's model. So, we are ready to test. So, this was simulated by primarily by Subhadeep Sadhu Khan in the lab. So, let me put his name, Subhadeep Sadhu Khan. So, kinetic energy injection rate is 0.1 and no, this was 0.2 I think. So, this is 0.2. So, there is one run without helicity. So, there is one epsilon h, this is injection rate. So, how much I am injecting? Okay. So, either point, so this kinetic energy is 0.1 and we do two runs, one no kinetic electricity injection and where injection is 0.2, I think it is 0.2. So, I will know in the next slide. Okay. So, we make these runs, we wait for steady state. So, these are forced runs, we inject all the time. So, you get a steady state and this steady state we can compute spectrum, flux and various. So, this is a spectrum of kinetic energy, this one, and this is a flux of kinetic energy. So, you see, so there is one run with 0 injection of helicity epsilon h 0 and one with 0.2. So, red is with 0.2 and green with no injection. So, green is no helicity and red is with helicity. So, there is some change in the left, but this 5/3 is not unchanged. And this, by the way, this is part which is coming from Pauw and this is same, it doesn't change. Okay. So, spectrum is, kinetic energy spectrum is the same. So, by the way, I derived last one is for helicity spectrum. Kinetic energy spectrum is unchanged in the dissipation range as well, is the same formula we did in hydro, Kolmogorov theory, and then I derived. What about kinetic energy flux? Is constant in the small region, but then it decreases, but it is unchanged again for both the runs. Red is helical and green is non helical, is unchanged. So, it is a very clear demonstration of the theory which said that helicity does not change the kinetic energy spectrum and kinetic energy flux in the inertial range at least. There is some change here, but in the inertial range is unchanged. Okay. I hope you are convinced, it's a good simulation. There are not many simulations done, there are some, but not very many. What about helicity? So, expect 5/3 with some corrections in the dissipation range. So, helicity is here. So, this for same run we compute helicity spectrum. So, this 5/3, but then there is a dissipation part, exponential part, 4/3 part. So, it is fitting very well, right. I mean, this is really nice. So, Pauw's for model, it just magically works, and the helicity flux is also very nicely fitting. We can also look at shell to shell. So, we look at shell to shell. So, non helical, which we did before, is forward, right. I mean, for any shell, diagonal is 0, off diagonal next neighbor is positive and lower left neighbor is negative. So, that is called local and forward. This property of 3D. So, this pure kinetic energy, and kinetic energy non helical we computed. Now, kinetic energy with helical is in this region, it is essentially same, except probably you can't see, but I can see from here, maybe you can see there is something happening here. Can you see the red yellow thing? So, there is some non local thing, but that is the forced range, the forcing is somewhere here. So, that is not the inertial range, but in the forcing region there is some helicity effect. Okay. And here too kinetic helicity is local and forward in the inertial range, but here there are some non local. Non local means long distance, local is you talk to your neighbor, you know, but no, otherwise I talk to long distance neighbors. Okay. So, this kinetic elasticity has bit of non-local component from the forcing band, and this is typically is interesting as concept which we need to investigate in more detail. From forcing range there is some non-local interactions. Okay. So, any questions on this so far?
The third one. The energy transfer is suppressed here. I mean HKC between forcing and
here the force
in third one. If you compare the second.
Acha, here there is some bit of yeah, there is some bit of suppression. Yeah. So, any other questions? Okay. So, I think this is the end of kinetic elasticity. Thank you.